Okay, good morning. Welcome back to day 2, acid-base chemistry. So today we're going to be doing some math. You will want to have your calculator handy, and we're going to be looking at pH and pOH. pOH is probably new to you. I don't think you've ever heard of that term before. By the end of today's lesson, you'll have it all dialed in. So I wanted to start off by showing you this interesting example. This is water. So if you had a glass of water full of water molecules, every once in a while, it says very slight, so less than 1/10000000th of a percent. So we'll just put less than 1% of the time, two water molecules can collide. And you learned yesterday that you can transfer a proton. An Arrhenius acid will give up a proton to an Arrhenius base. So if we had water reacting with water, if this water lost a proton, it would become OH minus, and if this water gained, it would become H3O plus. So it's a strange idea that in a glass of water, you can have an acid and a base, but because they are equal, they cancel each other out. So we don't say that a glass of water is acidic or basic because it has equal amounts of both hydronium ions and hydroxide ions. But it's just kind of a strange reaction and a weird way to look at a glass of water. Okay, so at 25 degrees Celsius, so what we call SATP, aqueous solutions can be classified as one of three things: neutral. If we're neutral, then we say that the concentration of hydronium, square brackets means concentration. So the concentration of hydronium is exactly 1 times 10 to the negative 7 moles per liter, which works out to a pH equal to 7. Any solution that's considered acidic has a concentration of hydronium ions that is greater than 1 times 10 to the negative 7, which results in a pH less than 7. And the last one, basic solution, hydronium ion concentrations are less than 1 times 10 to the negative 7, which produces a pH greater than 7. So this measure of pH, it stands for the potential hydrogen, or the power of hydrogen, is really a measure of the concentration of hydronium ions, because that's what makes you acidic. The more hydrogen ions you have, the more acidic, the lower your pH. And the less hydrogen ions you have, the less acidic you are, the higher your pH, greater than 7, 8, 9, 10. So the pH scale is based upon concentration of hydronium ions. And as I said, the more hydronium ions, the lower the pH, the more acidic. So let's take a look at this scale. I don't think you have this one in your notes. You have a different version. So neutral, the concentration of hydronium is 10 to the negative 7. As soon as you get a larger concentration, negative 6, 5, 4, 3, 2, 1, 0, you get more and more acidic. So 10 to the 0 means 1 mole per liter. 10 to the negative 1 is 0.1 molar. 10 to the negative 2 is 0.01 molar. You get the idea. 10 to the negative 5, 0.5 molar. So you can see we're getting more concentrated as we head down. And if you are basic, then you have less than that. So 10 to the negative 8 would be 0.1234567 0.000000001 moles per liter. And if you are 10 to the negative 14, you have almost no hydronium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So you can see that is a tiny, tiny concentration of hydronium, far less than 10 to the negative 7, which makes you basic. So on this chart, you have some acidic solutions, basic solutions, and then neutral right in the middle, distilled water, and you can see the corresponding pHs, with 7 being neutral in the middle. Now, this is a logarithmic scale, and what that means is it's log to the base 10. So if I am going to decrease 1 pH unit, that is a change in concentration of 10 times. That's important. So if I go from a pH of 3 to a pH of 2, my hydronium increases 10 times. If I go from a pH of 2 to a pH of 1, that's another 10 times. And if I go from a pH of 1 to a pH of 0, that's another 10 times. So my question for you is, if I go from a pH of 3 all the way down to 0, what is the increase in hydronium ions? Is it 10 plus 10 plus 10, or is it 10 times 10 times 10? And the answer is multiplied. 10 times 10 times 10 is 1,000. So from a pH of 3 to a pH of 0 is 1,000 times increase in hydronium ion concentrations. Or going the other way, basic, from 7 to 8, a pH of 1 is a decrease of 10 times, another decrease of 10 times. So from 7 to 9, or 2 pH units, is a decrease of 100 times acidic. It's 100 times less acidic, going from a pH of 7 to a pH of 9. So that is the pH scale, and I think this is the one that you have in your notes, which has the same information on it. pH, hydronium ion concentration, and it's got the formulas as well. Okay, now I'm just going to jump for a second to this PHET to show you guys this. So this is a pH of 7, and at a pH of 7, we have 1 times 10 to the negative 7 hydronium ions. You can see it right here. If I slide this up and increase the concentration of hydronium ions, you can see what happens. Oh, is it frozen? Frozen. No, come on. Okay, let's go this way. So as I increase the concentration of hydronium ions, I decrease the pH. And if you look at the picture here, you can see the red molecules represent hydronium and the blue represent hydroxide. So as the pH lowers, we are getting more and more and more hydronium, and you can see on this scale how the hydronium is increasing, and the solution is becoming more and more red. Okay, so hydronium ion is climbing, becoming more concentrated, and the pH is getting lower. We're down to 1. To go below 0, look at that. We can have a negative pH. Wow, shocking. And you get a negative pH when you have more than 1 mole per liter. So a pH of -1 is 10 moles per liter of hydronium. Interesting. Okay, let's jump back in. So your goal today is to be able to understand the pH scale, to understand that those increases of 1 pH unit are a 10 times increase or decrease in concentration, depending which way you're going, up the scale increasing in basic, down the scale increasing in acidity. And you have to be able to use these two formulas, which you must remember. So you have to be able to calculate the concentration of hydronium given pH, and you have to be able to calculate pH given concentration hydronium. So we'll go through those and I'll show you how they work. Okay, these are some questions in your textbook. Pure water has a pH of 7. What is the hydronium ion concentration when the pH is 7? So to calculate hydronium, we go 10 to the negative pH, which is 10 to the negative 7. Okay, that is the concentration of hydronium, or 1.0 times 10 to the negative 7. pH of 11, concentration of hydronium is 1.0 times 10 to the negative 11. So we're just using that formula. pH of 2, 1.0 times 10 to the negative 2 is the hydronium ion concentration. Okay, what if I'm given the hydronium ion concentration and I want to calculate pH? To calculate pH, we go negative log of hydronium. So pH would be negative log of 1.0 times 10 to the minus 3. Now, what does that look like in your calculator? It looks like, I gotta find it here. Where did I put it? Right here. Okay. Negative log. So we're hitting the negative sign right down here. Whoops, I did it twice. So negative, and the log button is right here. Negative log, so it's beside the 7. Negative log 1.0, and that was times 10 to the negative 7, I think. Let's jump back and see that. It was negative log 1 times 10 to the negative 3. Okay. 1.0. Now, for times 10 to that, I want you to use the exponent button, which is above the 7. It's EE. So we're going to go second EE, which gives us exponent negative 3. Finish off my brackets and hit enter. Whoops, I did 1.07. Darn it. Let's do that again. Negative log 1.0 second EE for exponent, negative 3. Finish the brackets, enter. Okay, a pH of 3. pH equals 3. All right, let's do one more. So 1.0 times 10 to the negative 5. So what is the pH when the concentration of hydronium is 1 times 10 to the negative 5? Negative log 1.0 times 10 to the negative 5. Okay, so negative, so that's the negative button down beside enter. Log beside the 7, negative log 1.0, and then I'm going second, the blue button, second. Exponent, EE, is just above the 7, and then negative 5. Finish off the brackets, enter, pH of 5. pH of 5. Okay, sig digs we'll talk about in a minute. If one water sample shows a pH of 3 and another shows a pH of 5, what factor do the hydronium ion concentrations differ? So to get from 3 to 5 is an increase of 2 pH units. Each increase is 10 times. So 3 to 5 would be 100 times decrease in hydronium ion concentration because it's getting less acidic, so it's decreasing. Okay, now let's do some more interesting examples. Communicate a hydronium ion concentration of 4.7 times 10 to the minus 11 as a pH. Okay, so here's our formula. pH is negative log concentration hydronium, 4.7 times 10 to the negative 11. So back to my calculator, 4.7 times 10 to negative 11. Negative log, it's beside the 7, negative log 4.7, darn it, how do I back up? Gotta start over. Negative log 4.7, second EE, second exponent. What was that number again? To the negative 11. 4.7 second exponent, negative 11. Enter. 10.3279. 10.3279. 10.3279. Okay, now let's talk about sig digs. This is going to drive you crazy. Okay, sig dig rules are really tricky for pH. Here's how they work. If I have a pH of 12.34 and I have a pH of 3.15 and I have a pH of 0.37, guess how many sig digs are in those pH numbers? Are you ready for this? It's crazy. This one has 2 sig digs. This one has 2 sig digs, and this one has 2 sig digs. So can you figure out the rule for sig digs and pH? It is only the numbers after the decimal place that count. So the 12 doesn't count, the 3 doesn't count, and the 0 doesn't count. Only after the decimal places. Now this is only for pH. It does not count. This is a regular number, 4.7 times 10 to the negative 11. So that has 2 sig digs. So if this has 2 sig digs, my pH is allowed 2 sig digs, which means 2 decimal places. So that becomes 10.33. Round the 7 rounds the 2 up to 3. And those are gone. So that is a pH value with 2 sig digs. Okay, second one, communicate a pH of 5.67 as a hydronium ion concentration. Okay, so the formula is concentration of hydronium equals 10 to the negative 5.67. So in your calculator, 10 to the negative 5.67. So for this one, 10 to the negative is located on the log button right beside the 7. It's the 10x. So we need to go second log, which gives us 10 to the x. So that was 10 to the negative 5.67. Enter. 2.1379. 2.1379. And that was times 10 to the negative 6. So that's the concentration of hydronium. Now, sig digs. So this is a pH unit. So for our sig digs, we're going with just the decimals. 2 decimal places. So this answer gets 2 sig digs. This is a normal number. So it will become 2.1 times 10 to the negative 6. Normal concentration, 2 sig digs. pH, 2 decimal places, 2 sig digs. Okay, so far so good. Hope so. All right, moving on. There are questions to practice, and we'll come back to these later on. So we'll hit those later for pH. Let's move on to pOH, the second half of today's lesson. So pH represents concentration of hydrogen ions. pOH represents the concentration of hydroxide ions. It's called the potential of hydroxide, or hydroxide ions. Should be a break there. Okay, so it's a measure of concentration of hydroxide. And it says here, remember that hydroxide concentration is inversely proportional to hydronium. What does that mean? Well, let's take a look at our scale. You will see that hydronium ion is way up here and hydroxide is down here. If it's going to let me do this. Oh, sure it is. As I start to add hydroxide ions, what happens to hydronium? You can see that as one goes down, the other goes up. So the red hydroxide ions are decreasing in concentration and hydroxide is increasing at the exact same amount. Now, when these things are exactly equal, we will have a pH of 7. So you're going to see that for a brief moment in time. I don't think I can pause this. Right there, 7. And now higher than 7, we have more hydroxide, less hydronium. Okay. So on our pOH scale, you will notice that if pH is 0, pOH is 14. They're opposites. If pH is 3, pOH is 11. As pH increases, pOH decreases. Increases, decreases. The last thing I'll mention about this is if you add the 2 up, you always get 14. 0 plus 14, 3 plus 11 is 14, 8 plus 6 is 14, 10 plus 4 is 14. So because they always add up to 14, they have to be inversely proportional. This one's 12, this has to be 2 to give us 14. Okay, so that's the pOH scale, which runs in the opposite direction of the pH scale. Battery acid is very acidic with a pH of 0 and a pOH of 14, whereas ammonia is very basic with a pH of 12 and a pOH of 2. Okay, pOH calculations look just like pH. So to calculate the concentration of hydroxide, it's 10 to the negative pOH. So what is the concentration of hydroxide ions? If we have a pOH of 6.3, we go 10 to the negative 6.3 on our calculator. That is, so the 10 to the x button is right beside the 7. So we go second log, which gives us 10 to the x. Negative, now I forgot my number, was it 6.3? Yep. 10 to the negative 6.3, enter. 5.0118, 5.0118. So concentration of hydroxide, and that was, forgot to grab the exponent, times 10 to the negative 7. Okay, sig digs. This is a pH or pOH. It's decimal places only, 1 decimal place. So we get 1 significant digit. 5 times 10 to the negative 7. Concentrations use normal sig dig rules. One number, 1 sig dig. Okay. Calculate the concentration of hydroxide. So our formula looks like the pH one, except it's pOH. So concentration of hydroxide is 10 to the negative pOH, which is 10 to the negative 1.50. So going back to our calculator, we go second log to get 10 to the negative 1.50, enter 0.0316, 0.0316. Dot, dot, dot. Okay, sig digs, only the decimal places. So that pOH has 2 sig digs. So this number gets 2 sig digs. 0.032 is the concentration of hydroxide. Okay, I want you guys to pause the video and do the next 3 on your own using your calculator. Calculate concentration of hydroxide using the pOH values given. So pause, try them, and then check your answers. Okay, so this one, that one was 2 sig digs, 2 sig digs, 2 decimal places, 2 sig digs. And this last one is 2 decimal places, 2 sig digs, 2.8 times 10 to the negative 12 mole per liter. Okay. Hey, we're almost done. Okay. So now you should be able to calculate hydroxide ion concentrations, calculate pOH given hydroxide ion concentrations. So here's our formula. The first example is right here. So pOH is, so just like the pH one, you go negative log of the concentration. Now this is a concentration. It's a normal number, 2 sig digs. So our pOH will have 2 decimal places. So it's negative log 0.27. Negative and log is beside the 7. Negative log of 0.27. 0.27, bracket, enter, 0.5686. 0.5686. 0.5686. 2 significant digits, 2 decimal places becomes 0.57. Is the pOH. What a mess. Let's try that again. which equals 0.57. Squeeze that in there. Okay, so I'll do one more and then I'll get you guys to try the next one. So the concentration of hydroxide is 4.5 moles per liter. That's 2 sig digs. So our pOH will have 2 decimal places. And again, the formula is negative log of concentration of hydroxide. So negative log of 4.5. Negative log 4.5. Negative 0.653. Negative 0.6532. Wow, you can have pOHs that are negative. You can also have pHs that are negative. Absolutely. Okay, so that was 2 sig digs, so 2 decimal places becomes, I wrote that in the wrong spot. It should be up here. Negative 0.65. 2 decimal places. Okay. I want you guys to try the last 2 on your own. There's your concentration of hydroxide. What is the pOH? So pause the video. Concentration hydroxide. pOH is negative 0.18 for pOH. 2 decimal places, 2 sig digs. This last one is 3 sig digs, so that means 3 decimal places. And when we plug that one in, pOH, we get 14.815. 3 decimal places. And yes, you can have pOHs greater than 14. So in Science 10, you were taught that the pH scale goes from 0 to 14. And the pOH scale goes from 0 to 14, but that's not true. In real life, it goes from almost -2 all the way up to almost 16. So it does exceed the 14 rule. Okay, last one, 3 sig digs, 3 decimal places. Oh my gosh, I just gave you the wrong one. My bad. That's this one, 14.815. This guy is 4.449. You're probably wondering what the heck I was doing. 3 decimal places, 3 decimal places for the 3 sig digs and the 3 sig digs. Okay, almost done. Hang in there. Lots of content today. Tomorrow's lesson is really short. Okay, pH and pOH. So you can convert from one to the other using this very simple formula. pH plus pOH equals 14. And I mentioned that already, that when you add up the pH and the pOH, where's our scale? They always add up to 14. Wow, I got to go way back here. So remember this, 0 plus 14 adds up to 14. Every one of these adds up to 14. If pH is 13, pOH has to be 1, and they add up to 14. Okay, so that's where the formula comes from. pH plus pOH equals 14. So if pH equals 2.5, then pOH is 14 minus 2.5 or 11.5. So that 11.5 plus 2.5 equals 14. If pOH is 11, then pH is 3. 11 plus 3 adds up to a pH of 14. And sig digs, they all had 1 decimal place, so they all have 1 decimal place. 1 decimal place, 1 decimal place, 1 decimal place. Okay, convert the following. So if pH is 6.7, pOH is 14 minus 6.7, which is 7.3. 1 decimal place, 1 decimal place. Okay. pOH is 2.9. pH is 14 minus, 14.0 minus 2.9, which is 11.1. 1 decimal place. And our last one, if pOH is 15, pH is 14 minus 15, negative 1. And there are no decimal places, no decimal places. And it is a negative. As I said, you can have pH and pOH that is negative. Okay, hey, we're done. Yay. So in your study guide, you have page 214 or 218 if it's Kelly, and I had that back on this screen. And there's also some textbook questions for additional practice. So they are all listed right here. And I'll make sure the answers are in Google Classroom for you to self-check those and make sure you're getting them right. So today's Tuesday. Tomorrow we get our last lesson of the week. And then Thursday, you're going to have a quiz on pH, pOH calculations, and all the acid-base stuff that we've learned so far, writing acid-base reactions. And that's a wrap. Okay, have a good day, everybody, and we'll see you tomorrow.